Hello everybody. Today we will discuss problems from US Physics Olympiad 2009, first round, F equal MA. But before that, please subscribe to this channel, because in that case you will get all problems and all solutions for US Olympia from 2007 till nowadays. So for this contest there were 25 problems, and that were given 75 minutes. So first problem: a 0.3 kilogram apple falls from rest through a height of 40 centimeters onto a flat surface. Upon impact, the apple comes to the rest in 0.1 seconds, and 4 square centimeters of the apple comes into contact with the surface during the impact. What is the average pressure exerted on the apple during the impact? Ignore air resistance. So let's go straight. First, to find what is average pressure, we need to use formula pressure equal average force over area of this impact. So to find what is force, we need to use second Newton law. In our case, that will be this formula: F equal delta P over delta T, where is delta P, that's a change of momentum for time delta T. In our case, a change of momentum, that's a total momentum before collision, because final momentum is 0. So that will be just P over dt. Now, to find what is momentum before impact, we can use formula momentum equal mass multiplied by speed. And the speed we can find from formula that speed equals square root from 2gh. That's a simple energy conservation. So finally we have this formula for pressure. Or we can use numbers. That will be solution. So we need to convert all units to SI units. It means that kilograms, centimeters to meters. Final result will be this one, which is approximately 21,000 Pascal. So that's the solution. B, correct answer. Problems 2 and 3. The following information is used for questions 2 and 3. 3 blocks of identical mass are placed on a frictionless table as shown. The center block is at rest, whereas the other 2 blocks are moving directly towards it at identical speed v. The center block is initially closer to the left block than the right one. All motion takes place along a straight horizontal line. Second problem. Suppose that all collisions are instantaneous and perfectly elastic. After a long time, which of the following is true? A. Center block is moving to the left. B. Center block is moving to the right. C. Center block is at rest somewhere to the left of its initial position. D. Center block is at rest at its initial position. And E. The center block is at rest somewhere to the right of its initial position. Answer. Let's look what happened here. So first, because this left block is closer to center block, they will collide before this collide, right one collide. So after collision, they will exchange their velocity because they have the same mass, and this block, right block, will stop, and the center block will go to the right with the speed v. After that, it collides with the left block. They will exchange velocities, and now the right block going to the right and the center block going to the left, and it will meet this left block exactly in the same place when they first collide. But now this block, center block, is moving to the right, and the right block is in rest. So they will exchange velocity, and the left block will go to the left, but the center block will stop exactly in the same place as it was initially. So the correct answer is D. Next, problem 3. Suppose instead that all collisions are instantaneous and perfectly inelastic. After a long time, which of the following is true? A. The center block is moving to the left. B. The center block is moving to the right. C. The center block is at rest somewhere to the left of its initial position. D. The center block is at rest at its initial position. E. The center block is at rest somewhere to the right of its initial position. Solution. Because all collisions are perfectly inelastic and total momentum of whole system is 0, it means that after all collisions they will stop to move somewhere. It means that center block will not move. But what happened? First collision will be with the left block and center block. After this collision they start to move to the right, and after that they will collide with the right block somewhere to the right from center block initial position, and they will stop there. So it means that the correct answer is E. The center block is at rest somewhere to the right of its initial position. Problem number 4. A spaceman of mass 80 kilograms is sitting in a spacecraft near the surface of the Earth. The spacecraft is accelerating upward at 5 times the acceleration due to gravity. What is the force of the spaceman on the spacecraft? Solution. To solve this problem, we need to use second Newton law. This is our equation. The ma equal normal force minus force of gravity, because normal force acting up and the gravity acting down, and acceleration equal 5g. So from here we can find what is normal force. That will be this one. This is normal force which is acting from a spacecraft to spaceman. But with the same force he is acting on a spacecraft. And the solution is A. 4,800 newtons. Problem number 5. 3 equal mass satellites A, B, and C are in coplanar orbits around the planet as shown in the figure. The magnitudes of the angular momenta of the satellites as measured about the planet are LA, LB, and LC. Which of the following statements is correct? We have to choose one of 5 of these statements. Solution. Let's check this picture. We have to write definition for angular momentum. That's this one. Angular momentum equal mass multiplied by velocity and cross product with the radius vector to this satellite from planet. But when vector of velocity and radius vector perpendicular to each other, we can use this equation. And here we can check what is the difference between orbits of these three satellites. So first satellite A, it has a circular orbit, and let's compare this angular momentum with the momentum of B satellite. In this point, this satellite B has less velocity than satellite A and same radius vector. It means that angular momentum greater for satellite A. All angular momentum they are conserved, so it doesn't matter where do we measure it. So we just established a first relation. Now let's compare angular momentum of satellite B and C. But now we can choose this point. In this point, velocity of C it's related to circular orbit of this C satellite, but B satellite has a greater velocity because it's the orbit is going by ellipse, which is greater than this circle. That means that angular momentum for B greater than for C. And we can just write this relation that LA greater than LB greater than LC. This is the answer for problem 6. An object is thrown with a fixed initial speed v0 at various angles alpha relative to the horizon. At some constant height h above the launch point, the speed v of the object is measured as a function of the initial angle alpha. Which of the following best describes the dependency of v on alpha? Assume that the height h is achieved and assume that there is no air resistance. A. V will increase monotonically with alpha. B. V will increase to some critical value V max and then decrease. C. V remain constant, independent of alpha. D. V will decrease to some critical value V minimum and then increase. E. None of the above. Solution. Here we have energy conservation. So it means that it doesn't matter which angle we will use here, because the energy is conserved, and we have a formula v square equal initial v0 square minus 2gh. And in this formula, the speed on height h does not depend from angle. So solution will be C. V will remain constant and independent of alpha. Problem number 7. The bird is flying in a straight line, initially at 10 meters per second. It uniformly increases its speed to 15 meters per second, while covering a distance of 25 meters. What is the magnitude of the acceleration of the bird? On the left we have 5 different choices, so we need to solve this problem and pick a good one. Solution. What is known here is that this motion is with a constant acceleration, and also we know what is initial speed, what is final speed, and what is distance. It means that we can use formula number 4 in kinematics, which is not including time, and this formula looks like this. Final speed square equal initial speed square plus 2AD, 2 accelerations multiplied by distance. From this formula we can immediately find what is acceleration. Here we have a formula for acceleration, and we have, after we put numbers, we have acceleration equal 2.5 meters per second square. Problems number 8 and 9. The following information is used for questions 8 and 9. A flat disk rotates about an axis perpendicular to the plane of the disk and through the center of the disk with an angular velocity as shown in the graph below. Question 8. Determine the angular acceleration alpha of the disk when time t equal 2 seconds. Solution. We have a graph, angular velocity versus time. And from this graph we can find what is instantaneous acceleration just using slope for this graph. But here we have a straight line. It means that angular acceleration everywhere is the same. So we can just count what is the slope of this line. We can take, let's say, angular velocity for time 2 seconds and for time 0 seconds. And we can use formula change of angular velocity over change of time. That's angular acceleration. And in our case it's equal 0 minus 4 over 2, which is negative 2 radians per second square, which is answer D. Question number 9. Through what net angle does the disk turn during the 3 seconds? So here we can use another equation. We can use average angular velocity for motion with a constant angular acceleration. In that case we can use formula this one, average velocity plus final velocity over 2, that's average velocity multiplied by time. We can choose time from 0 to 3 seconds. This is in our question, and put this angular velocities. Initial it's 4 and final is negative 2. So that will be solution. Negative 2 plus 4 over 2 multiplied by 3. That will be 3 radians. Correct. Problem number 10. A person standing on the edge of a fire escape simultaneously launched 2 apples, one straight up with a speed of 7 meters per second and the other straight down at the same speed. How far apart are the 2 apples 2 seconds after they were thrown? Assuming that neither has hit the ground. Solution. In this kind of problem, best way to do is to choose a proper frame of reference. In this case, we can choose a frame of reference which is start to move down with the acceleration g. In that case, in this frame of reference, our apples will move with constant velocities. One is straight up with the speed 7 meters per second and the other straight down with the same speed. So relative speed will be 14 meters. It means that for 2 seconds they will be apart 28 meters. So that's the solution. C is correct answer. Problem number 11. A 2.25 kilogram mass undergoes an acceleration as shown on this graph. how much work is done on the mass. Solution. First, let's write equation for work. If we have a graph acceleration versus distance, we can immediately write this equation, that work done by force F on a small distance dx equal this expression, and because mass is constant, we can take it out, and we have dw equal mass multiplied by acceleration multiplied by dx. If we look at this graph, we can see that acceleration multiplied by dx, this is just area with displacement dx and current acceleration. So to find what is total work done by this during this graph, we can count what is total area and multiply it by mass. That will be solution. Let's count this area. From 0 to 2, that will be area for this triangle, which is 4. After that, this area from 2 to 4, which is 8. And after that, area of this triangle, which is 4 by 4 over 2, which is 8. So total is 20. And here we have negative area, which is area of this triangle, that's 4. So we have to subtract from 24, that will be 14. And the final result will be this one. Work equal mass multiplied by total area, which is 2.25 multiplied by 16, and the result is 36 joules, which is answer A. Problem number 12. Batman, who has a mass of big M, 100 kg, climbs to the roof of 30 meters building, and then lowers one end of a massless rope to his sidekick Robin. Batman then pulls Robin, who has a mass of small m equal 75 kg, up the roof of the building. Approximately how much total work has Batman done after Robin is on the roof? Solution. Here it doesn't matter which way they will climb. The result is just work done against gravity. So we just need to find how much potential energy were increased by work done by Batman. So that will be total mass multiplied by g, acceleration of free fall, and multiplied by height of building. So that will be this formula. And now we can put numbers and we will get approximate answer 5 multiplied by 10 power 4, which is a C, correct answer. Problem number 13. Lucy, mass 33.1 kg, Henry, mass 63.7 kg, and Mary, mass 24.3 kg, sit on a lightweight seesaw at evenly spaced 2.74 meter intervals in the order in which they are listed. Henry is between Lucy and Mary, so that the seesaw balances. Who exerts the most torque in terms of magnitude on the seesaw? Ignore the mass of the seesaw. Solution. In this problem, we don't even need to calculate anything, because let's say we have a point of balance exactly in point of Henry. It means that Lucy will create a greater torque than Mary, and there will be no balance. Seesaw will go counterclockwise if Lucy at the left and Mary at the right. So now we need to move this point of balance a little bit to the left from Henry. And in this position, when we find this point, it means that Lucy creates the same torque as Henry and Mary together. It means that Lucy creates the greater torque than anybody of Henry or Mary. So that's the solution. B is correct answer. Problem number 14. A wooden block of mass M is hung from a peg by a massless rope. A speeding bullet with mass small m and initial speed v0 collides with the block at the time t equals 0 and embeds in it. Let S be the system consisting of the block and bullet. Which quantities are conserved between time negative 10 seconds and time positive 10 seconds? Solution. Let's investigate all 5 possibilities. A. The total linear momentum of system. Before collision it's conserved, but after collision, when this system starts to rotate around this peg, there is a force acting on this peg and bullet, which is changing total linear momentum and horizontal momentum. So it means that not A, not B are good answers. C. The mechanical energy. Mechanical energy is not conserved because here we have absolutely inelastic collision and we will lose some energy during this collision. D. The angular momentum of a system as measured about a perpendicular axis through the peg. It's conserved before collision, but after collision, when this system starts to rotate counterclockwise, we have gravity force which acting clockwise, so it's changing angular momentum, and D is not correct answer. And answer E, none of the above are conserved, which is true. So correct answer is E. Problem number 14. A 22 kg suitcase is dragged in a straight line at a constant speed 1.1 meters per second across a level airport floor by student on the way to the 40th IPHO in Merida, Mexico. The individual pulls with a force F equal 100 newtons along a handle with makes an upward angle of 30 degrees with respect to the horizontal. What is the coefficient of kinetic friction between the suitcase and the floor? Solution. First, let's draw the free body diagram. Because this suitcase moving with a constant speed, it means that this is the situation of equilibrium. So we have to write horizontal and vertical equations for equilibrium. Let's do this. So first we have horizontal force F acting at angle phi equal 30 degrees, and we have force of friction acting opposite side. So this is the equation. We have force of friction equalize force F, pulling force F multiplied by cosine phi. Second equation, that's vertical. We have force of gravity mg, which equalized by normal force and vertical part of pulling force. So that will be this equation: mg equal F sine phi plus normal force. And next one is relation between normal force and force of friction. Because this body is moving, it means that we have this equation, that force of friction equal coefficient of friction multiplied by normal force. Now let's exclude some components. So first we can take normal force from this equation and insert it here. So we have force of friction equal coefficient of friction mu multiplied by mg minus F multiplied by sine phi. And now we can insert this expression for force of friction in this equation. And after that we can express a coefficient of friction from this last equation. So we have this expression, that coefficient of friction equal force F multiplied by cosine phi and divided by mg minus F sine phi. The last step is to put all numbers, and after that we can count that this coefficient approximately equal 0.51, which is close to answer C. So C is correct answer. Problem number 16. Two identical objects of mass m are placed at either end of a spring constant k, and the whole system is placed on a horizontal frictionless surface. At what angular frequency omega does the system oscillate? Solution. Let's draw this picture. On this picture we can see that if we put the system on oscillation, the center of mass will not move. It means that we can split this system by half, and each half will oscillate like independently, because this wall is not moving. It means that we have from the right we have system with the mass and spring with constant 2k, and on the left the same thing. So it means that both masses will oscillate with omega equal square root from 2k over m. Correct answer is B. Problem number 17. You are given a standard kilogram mass and a tuning fork that is calibrated in Hertz. You are also provided with a complete collection of laboratory equipment, but none of it is calibrated in SI units. You do not know the value of the fundamental constants. Which of the following quantities could you measure in SI units? A. The acceleration due to gravity. B. The speed of light in vacuum. C. The density of room temperature water. D. The spring constant of a given spring. E. The air pressure in the room. Solution. Because we have a calibrated tuning fork, we can measure frequency for some equipment. And here we have mass, and also if we check all 5 answers, we can see that the number D has a spring. So we can connect the mass to spring, connect it to fork like this, and measure what is the frequency of oscillation of this system. From this frequency we can find what is a constant K. This is the formula how to find what is a constant K. So correct answer is D. Problem number 18. A simple pendulum of length L is constructed from a point object of mass m suspended by a massless string attached to a fixed pivot point. Small peg is placed a distance 2/3 of L directly below the fixed pivot point, so that the pendulum should swing as shown in the figure below. The mass is displaced 5 degrees from the vertical and released. How long does it take to return to its starting position? Solution. Let's analyze this motion. First, if we had initial angle 5 degrees, that's small. It's like a small oscillation, almost a harmonic oscillation. And when we reach this pivot, here the maximum angle will be around 15 degrees, which is small enough for oscillations. So we can just estimate this motion like this. So first we have quarter long period when this pendulum swung through this construction, but when this string reached this peg, it starts to oscillate like this with a length of just 1/3. And now we have another quarter of period, but small period. After that, this pendulum swung back for a quarter of a small period, and after that it's get back again for a quarter of a long period. Totally we have 2 quarters of a long period and 2 quarters of a short period. Let's write equations for long period. That will be a half long period. And also we have half of a short period. That's this one. And now we can count what is total time to move from this point back to this point. That will be this expression. So if we look at this expression, that's exactly E answer. So correct answer is E. A certain football quarterback can throw a football a maximum range of 80 meters on level ground. What is the highest point reached by the football if thrown this maximum range? Ignore air friction. Solution. Here we can use 2 formulas. One is for range and other for height. For range we have this formula. If a ball was thrown under angle theta with a speed v, so the total range d will be like this, and the total height will be like this. Now we can divide height by range, and we will get this formula. And now we can use this formula to solve this problem, because for maximum range we have angle equal 45 degrees, and tangent 45 degrees, it's 1. So it means that height 4 times less than range, and the solution is 20 meters. Problem number 20. Consider a completely inelastic collision between 2 lumps of space glue. Lump 1 has mass m and originally moves directly north with a speed v0. Lump 2 has mass 3m and originally moves directly east with a speed v0/2. What is the final speed of the masses after the collision? Ignore gravity and assume the 2 lumps stick together after the collision. Solution. Here we can use momentum conservation, and let's just count what is initial momentum and equalize it to final momentum. Initial momentum. In the x direction we have this expression. We have mass 3m multiplied by v0 over 2, that's momentum in x direction. Momentum in y direction, that's mass m multiplied by v0. And now we can count what is a total momentum of system, which is just a square root from squares of both momentums, which is this expression. And now to count what is total speed, we just need to divide this momentum by total mass of these two pieces which moving together. And that's a result. As we can see, correct answer is C. Problems 21 and 22. The following information is used for questions 21 and 22. Two stars orbit their common center of mass as shown in the diagram below. The masses of the two stars are 3m and m. The distance between the stars is d. Question number 21. What is the value of the gravitational potential energy of the two-star system? And question number 22. Determine the period of orbit for the star of mass 3m. Solution. Gravitational potential energy of two objects equal this expression. That's a negative g multiplied by m1 multiplied by m2 and divided by distance between objects. In our case, that will be negative 3g multiplied by m squared over d. Question number 22. Determine the period of orbit for the star of mass 3m. Solution. Force of gravity between these two objects equal this expression. 3g multiplied by m squared over d squared. But from other hand, mass 3m rotating around a common center of mass, which is on a distance 1/4 d from this big mass, and it's equal to total mass multiplied by v squared over a radius, and the radius is 1/4, so that will be 12m v squared over d. And from here we can find what is speed of this big mass. That's this one, 1/2 square root from gm over d. And now to find what is period, we just need to use this formula. Period equal to pr over v, where r is radius of orbit. In our case it's 1/4 d, and v is already counted. So finally we have this result, which is correct answer A. Problem number 23. A mass is attached to an ideal spring at time t equals 0. The spring is at its natural length and the mass is given an initial velocity. The period of the ensuing one-dimensional simple harmonic motion is t. At what time is the power delivered to the mass by the spring first a maximum? Solution. To solve this problem, let's just write the equation for harmonic motion for this mass. Using initial conditions, we can write it like this. Displacement equal amplitude multiplied by sine omega t. Second, we can count what is velocity, just to take a first derivative by time. That will be this expression, a omega cosine omega t. Second, we do a second derivative to find what is acceleration. That's negative a omega square sine omega t. And now we can count what is power. Power equals force multiplied by velocity. This one. So force equals mass multiplied by acceleration. And using these two formulas we can count what is power. That's negative 1/2 a square omega power 3 sine 2 omega t. And now we need to find what is at what time first this power has a maximum. That's obviously for sine 2 omega t equal negative 1. This one. And the first time it happened when 2 omega t equal 3 over 2 pi. And from here we can immediately find the moment when this power has a maximum. This is the solution. So time equals 3 over 8 period. Here in these 5 answers we have to pick the correct one. Correct one is D. Time equals 3 over 8 t. Problem number 24. A uniform rectangular wood block of mass big M with a length b and a height a rests on an incline as shown. The incline and the wood block have a coefficient of static friction mu s. The incline is moved upwards from an angle of 0 through an angle theta. At some critical angle the block will either tip over or slip down the plane. Determine the relationship between A, B and mu s such that the block will tip over and not slip at the critical angle. The box is rectangular and A not equal B. Solution. Let's draw the picture for a critical position when angle is critical and block is not yet tipped over but almost ready. So that's the picture. I can remind you that critical angle is an angle for which this block start to slip when tangent theta equal mu static. And also critical position here because we have a center of gravity, which is center of mass, and the vertical line going through this center of mass is going exactly through one corner of this block. It means that after it will move a little bit further, it will slip over because there are no support from base of this cube. It means that we can just count what is the geometry for this picture. Here we have angle theta, which is critical, and also we have angle theta here because we have two perpendicular lines which are forming these two angles, and the tangent of this angle theta in a cube exactly equal b over a, and we know that this tangent equal mu static. So this is our formula. It means that this cube will tip over when tangent theta or mu static greater than b over a. That's the answer for question, which is C. Problem number 25. Two discs are mounted on thin, lightweight rods oriented through their centers and normal to the discs. These axles are constrained to be vertical at all times, and the discs can pivot frictionlessly on the rods. The discs have identical thickness and are made of the same material, but have differing radii r1 and r2. The disks are given angular velocities of magnitude omega1 and omega2 respectively, and brought into contact at their edges. After the disks interact via friction, it is found that both disks come exactly to a halt. Which of the following must hold? Ignore effects associated with the vertical rods. Solution. First, we can write equation how is angular momentum changing during time. Suppose that force of friction Fj act on both disks for the time delta Tj. They act to each disk, so these two forces, they are equal to each other. And the change of angular momentum equal this expression: force multiplied by radius multiplied by delta time. And I equal 1 or 2. That's correct for both disks. Now we can summarize all this interaction till both disks came to halt. So it means that total change of angular momentum equal total initial angular momentum. It means that we have this formula. So for both I, we have this sum the same for both disks. It means that we can divide this angular momentum for first disk by angular momentum for second disk and have this relation. What are this initial angular momentum for both disks? They are like this. Angular momentum equal I multiplied by omega, and the I equal 1/2 mass r square, and because mass is proportional to radius square, we have this formula, and finally this is the expression for angular momentum. Now we can divide this angular momentum for the first disk to angular momentum for second disk and equalize it to this expression. So after dividing this L1 over L2 for this expression, we have this relation, and it's equal to initial relation R1 over R2. We can cancel one time R1 and R2, and finally we have this relation. We have R1 cube multiplied by omega 1 equal R2 cube multiplied by omega 2. This is the solution. And that's answer number D. Correct answer.